A very good morning to our Honorable Vice Chancellor, Professor Dr. Vishwajay Chatterjee, Provost Sir, Professor Dr. Pradeep Kumar Sharma, Dean Sir, Professor Dr. Anirudh Mukherjee, HOD Sir, Department of Electronics and Communication Engineering, Professor Sandeep Das Sir, and other dignitaries. I, Diba Chakravati from the Department of Electronics and Communication Engineering, would like to take the privilege to declare that this IEI Student Forum of the University of Engineering and Management Jaipur is organizing the webinar today on Reconfigurable Architecture for Software Defined Radio and Beyond. Now, a brief introduction of IEI. The Institution of Engineers India (IEI) is a statutory body to promote and advance the engineering and technology established in 1920 and incorporated by Royal Charter in 1935. It is the largest multidisciplinary professional body of engineers encompassing 15 engineering disciplines with a corporate membership of over 2 lakhs and serving the nation for more than 9 decades. The IEI has its headquarters located in Kolkata with national presence through more than 100 centers and several overseas chapters, forums, and organs. IEI has been recognized as a scientific and industrial research organization by the Ministry of Science and Technology, Government of India, and besides conducting its research, provides grant in aid to UG, PG, PhD students of engineering institutes and universities. Now, I would like to request our Honorable Vice Chancellor, Sir, to give his few words of encouragement.
Thank you, Dibbo. Dibbo is our student. See, he nicely conducted it. It's a privilege for us that today we have with us Professor Dr. Amitabha Sinha. Now, when Dibbo will be reading out his entire short CV, you will find that it will need around 5 minutes or 10 minutes to read the entire achievements that Professor Dr. Amitabha Sinha has done throughout his career. So I will not get into that, but I will just tell only one thing, which I believe will summarize his contributions. See, when I was doing my engineering and I was actually getting into this engineering field, getting into my professional life, I saw him, and he was a person at that point of time. He was teaching entire Bengal and also maybe entire India that you can actually build a chip in which you don't need to build the circuit yourself. You can program the circuit and put it inside that chip. This concept at that time, people were just trying to put in themselves. It was not an established fact at that time. But Professor Dr. Amitabha Sinha was actually teaching entire Bengal and maybe entire India that yes, it is possible. You can build the chip only by writing programs, and then the program can be built inside the chip. You don't need to get inside the circuitry of that. So this is how I came in touch with him and I got to know him. It's a privilege that I'm again able to listen to him, and the topic he has chosen FPGA based reconfigurable architecture for software defined radio and beyond. So you can see that he has brought in FPGA, and the architecture also is reconfigurable. That is, the chip architecture might be reconfigurable, and radio also, software defined radio is there. So there are many topics within that. So I'm extremely interested to hear that, and I will be very eagerly hearing everything, and I'm sure that all the attendees over here are excited. And you can post your questions in the questions box, and once this session is over, we will be taking those questions, and I'm sure that sir will be answering those questions one by one. So I don't have much more to say today. Thank you so much. Thank you, Dibbu, and thanks to all the attendees for coming over here. Thank you, Professor Dr. Amitabha Sinha, for agreeing to come over here. We are privileged again. Thank you so much. Dibbu, again, it's over to you.
Thank you, Professor Chatterjee, for introducing.
Thank you. Thank you so much, sir.
Today we have Professor Amitabha Sinha with us. Professor Amitabha Sinha has been working in the industry, premier academic institutes, research and development centers, and IT telecom organizations in India and abroad for more than 35 years. And his areas of research include embedded system design, VLSI design, digital signal processing, reconfigurable architecture using FPGAs, software-defined radio, processor architecture, and system-on-chip design, advanced computer architecture, etc. Professor Sinha is currently working with MAKAUT, as UGC Adjunct Faculty and Director, Academic Reforms. He was a senior faculty member of the Department of Computer Science and Engineering, Bengal Engineering College, now Indian Institute of Engineering, Science and Technology, West Bengal, India, during 1985 to 1991, and Department of Computer Science and Engineering, BITS Pilani, during 1997 to 1998. He was visiting faculty, Department of Computer Science and Engineering, Oakland University, USA during 1994 and 1999, and was an expected faculty member of a premier Malaysian university, Mara Institute of Technology during 1994 to 1995. Professor Sinha was a professor and director of School of Engineering and Technology, West Bengal University of Technology from 2005 to 2012. He also held the post of Principal Director of different engineering colleges affiliated to Maulana Abdul Kalam Azad University of Technology, formerly WBUT. Professor Sinha was the Senior Manager and DSP Group Head of the R&D Center Hyderabad and Regional Manager Education and Training Kolkata of CMC Limited. During 1991 to 1997, he was the Vice President Research and Development of HFCL, one of the leading telecom companies in the country from 1998 to 2003. Professor Sinha has had chaired a number of conferences, including IEEE, and delivered invited talks in India, USA, Singapore, China, Germany, Russia, Australia, and Hong Kong. He has guided more than 100 MTech students and a number of PhD students. He had published more than 80 research papers in reputed international journals and conferences. He has co-authored 4 books published by Lambert Publishing, Germany. He was a member of advisory board of the Department of Science and Technology, Government of West Bengal. With a graduation in Electronics and Telecommunication Engineering from the premier Engineering Institute, Bengal Engineering College, Jaipur, now IIEST in 1976, and a post-graduation in Electronics from University of Kent at Canterbury, UK in 1978, Professor Sinha holds a doctoral degree in Computer Science and Engineering from Indian Institute of Technology, IIT Delhi, which he had obtained in 1984. Professor Sinha is a fellow of the Institute of Engineers and the recipient of obtained Indian Leadership Award for Education Excellence from Indian Economic Development and Research Association, New Delhi, India 2013. Now I would like to request Professor Dr. Amitabha Sinha to carry on to the webinar.
Thank you, Dibbo, for your introductions.
Thank you, sir.
Okay. So the topic is FPGA-based reconfigurable architecture for software-defined radio and beyond. Now, when we talk about software-defined radio, then first we should understand what do we mean by the conventional radio and why we are going for software-defined radio. Now, in a conventional radio, basically it's a hardware device where different signal processing functions and communication functions are basically fixed. So a set of hardware elements perform digital signal processing operations for communicating with its wireless network. So here, in fact, the devices, all these things are fixed. You can't change it. That is a conventional radio. I believe many of you might not have seen the conventional radio, but the old people like me, we must have seen the radio, conventional radio, where by tuning we change the stations, okay, and we have fixed communications media like medium wave, short wave, and that we have to change by changing the switch. That's all. And let's have a look at how the radio receiver functions. First, from the antenna, the signal will be received, and that will go to the input of RF amplifier, radio frequency amplifier. Because the signal level is very small, so RF amplifier will amplify that signal. And there must be a local oscillator where this signal will be multiplied with that. Then there's a mixer stage which translates the desired input signal to the IF frequency. Then demodulator recovers the original modulating signal, and this goes to the input of the audio amplifier, and the speaker will be there, and we can hear the sound. But what are the drawbacks of the conventional radio systems? that we're trying to go for software-defined radio. That has to be made very clear. Now, the conventional radio, they are based on the hardware systems which have limited utilities. And just a minute here. One second. It's not. Well, so here conventional hardware-based radio systems have limited utilities, signal parameters defining the modulation methods, waveform, signal generators, and link layer protocols are fixed. So they are inflexible in the sense they are based on particular modulation methods and systems which cannot be changed, which are fixed in that particular hardware. But these days, due to the rapid evolutions of wireless communication systems from 2G to 3G to 4G, in fact, the equipment manufacturers, they are facing tremendous problems because of the incompatibility of the equipments. And different link layer protocols are different. For example, for 2G, the protocols are different. For 3G, the protocols are different. So here what is happening, even the service providers, they are facing the problem. And rapidly they have to change with that. And different wireless communication technologies are deployed in different countries or continents. There is also again a problem. Like when you are carrying a mobile handset from here to some other country, it may so happen that it might not operate because of the incompatibility. So these problems cause difference in the deployment of global roaming services and in rolling out new services due to widespread. So the problem is the technology is advancing. We are going from 2G to 3G and all. At the same time, your base stations, they need to be changed. And that's a huge cost. So how to come up from that kind of problem? And if we need to come out from that kind of problem, then we have to find out some kind of innovative solutions. Like due to the technological advancement, perhaps the mobile handsets, rapidly we can change it. The cost of mobile handset is relatively much smaller compared to the base stations changing cost. So why? So in fact, here we need the flexibility. And why? Unique hardware platform for several products, shorter design time to support multiple standards like GSM, CDMA, etc. And it can be modified in the future without any hardware change. So the requirement is in different country, different kind of communication protocols are there. Like here we have GSM protocol. In the United States or in entire North America is based on CDMA. So here, the changing of technological changes, how that can be achieved without changing the hardware. That is the impact expectation in today. So rapid software bug fixing, that is also very much required, is expected to be the key value propositions for handset market, especially in 3G markets. And in long term, the economy, which is the most important factor and which is the driving force. That means we need some kind of software approach. So easier to manage after selling. So software-defined radio aims to overcome these limitations of the conversion of the radio systems by building the flexible open architecture-based radio system. So without changing the hardware, the technological changes will be incorporated by software. That is the whole idea behind software radio. So functional modules of the radio system, such as modulation, demodulation, signal processing, signal generation, coding, link layer protocols, all are implemented on generic, reprogrammable, reconfigurable hardware platform using software. Like, for an example, let's take the example of amplitude modulations. So amplitude modulation is what? Basically, multiplication of carrier signal with the baseband signal. Now, this multiplication will be done by software, easily can be done, because the signals, they can be sampled, they can be quantized, they can be digitized, and a digital platform will be doing that task. So any task which is being done by hardware can easily be implemented by software with the proper facilities. So that is the whole idea. That means the radio systems will be built by software, keeping the hardware platform safe. So when the technological advancement will be coming, so that advancement will be incorporated by changing the software. The concept goes beyond cellular base stations to other keys of the radios, such as handheld devices that can switch from one network to another network. So entire thing can be done by software. That is the whole idea. So SDR is able to interoperate with different wireless protocols, incorporate new services, and upgrade to new standards. So here's the digital receiver. Earlier, I gave you the example of a conventional radio systems, which is analog radio receiver. Now here, you can see that the antenna RF amplifier picks up the signal and just enhances the signal level. The RF translator will translate to RF level. Then A to D converter will sample and it will convert it to digital values. And here, the local oscillator will generate sine and cosine signal, because we know that e to the power j theta equal to cos theta plus j sine theta. So cosine and sine both will be required. Then it will go through a digital low-pass filter, then demodulations, a DSP activities will be done, then again D2A converter, and that will go to the input of the audio amplifier. Okay. And this is architecture of a generic digital radio receiver, hence receiver and transmitter. So same antenna will serve the purpose of receiving and transmitting. So the front end is the RX and TX, stands for receiving and transmission. And here A to D converter, convert the analog to digital, then digital down converter. Digital down converter is what? When in fact we receive the signal which has been transmitted, we have to demodulate it. Demodulation means to extract the baseband signal. That means it is a down conversions. The baseband signal frequency is much less compared to the carrier frequency. Then the baseband processing will be done, and finally it will go to the input of the loudspeaker or headphone. And this is the reverse process. Okay. Digital up conversions, then digital to analog converter, and finally it will be transmitted. So this is the impact the mobile systems or any receiver systems. Okay. So this is a local oscillator I have already described. So software download for reconfiguration. So the software-defined radio forum defines the term, the radio software download, as the process of delivering reconfigurable data, now new executable code to an SDR device. So radio software consists of primarily radio software. So basically the whole idea is the reconfiguration can be done by downloading the software. Okay, and how this software will be downloaded, I'll be describing the subsequent. Now the question is how to implement it. We are talking about software-defined radio. We understand that this will be done by software. So earlier, the conventional radio system, the task will be converted to the software and it will be done by that. But how it could be done by software? Now, so here the issue of the implementations. There are three possible options for implementing software-defined radio. One is the DSP processor. Another is SOC or ASIC. SOC stands for System on Chip, or ASIC, Application Specific Integrated Circuits. And FPGA, today, this is the most popular programmable device, field programmable gate array. And what is the challenge in today's market? Look, we the scientists, we develop many things in the laboratory, but at the end of the day, we must have to consider that there must be the sellers, whether your innovation can reach to the customer. So two important things are there. Product must exceed customers' expectations. That means customers will not be merely happy, they should be delighted. That is in fact the key factor for selling a product. And it has to be brought to the market quicker than ever. Only you are doing paper research day after day, but by that time your competitor will come to the market. So you have to come to the market quicker than ever. That is also very, very important. And today the way the technology is changing, you must have noticed that today perhaps you have purchased a very powerful mobile handset and you are showing your friends, hey, I have got it. After 6 months, when you will find that your friend has purchased a mobile system much better than yours at half the cost, then you will be frustrated. So in fact, the lead time is very small. Obsolescence time is very, very small. So when you are developing a product, you have to come to the market very fast. So your development and all these things, this time has to be reduced substantially. So let's see the issues. So issues involved in designing software-defined radio using state-of-the-art VLSI devices. It has to be low cost, power should be low, low power dissipation, high speed like Sputnik, and flexible. So these 4 issues, in fact, govern the design of software-defined radio. Because low power dissipation is very important because of 2 reasons. One is most of the electronic devices, their failure is because of the heating effect. And another thing, perhaps you might be purchasing a very powerful mobile handset in your pocket, and you can't afford to tolerate that amount of heat, that you have to use a cooling fan in your pocket. You can't do it. Or secondly, you can't go to your place after every half an hour to charge your mobile. So low power is the most important thing. And cost is needless to say, and speed has to be very high. Because today we are thinking, especially when we are thinking about software-defined radio, which is operating at the gigahertz level, then speed is very, very important, and it has to be flexible. Because whatever we have purchased today, same mobile handset should be in use tomorrow just by changing the software, keeping the same hardware. So that is the thing, in fact, that is the need of the hour. Now let's have a look at, we have already discussed that we have 3 possible options for implementing software-defined radio. One is the DSP processor, then ASIC and FPGA. So let's have a look at what DSP processor is. DSP processors are basically microprocessors, but they are optimized for DSP applications, digital signal processing applications. Now, these communication systems are basically based on the signal processing functions. So these DSP processors are useful for that, apparently. But let's have a look at how the DSP processors, they operate. Any particular function, we write the software for that. Software means what? A program. What is a program? A sequence of instructions which will be executed step by step, one after one. That means they will be executed sequentially. And sequential things are always slower because step by step they'll be operated. So more is the complexity of the algorithm, more will be the number of instruction sets, and more will be the execution time. Now, even though today there are advanced DSP processors come to the market, like most of the DSP processors are Harvard architectures. Now, modified Harvard architecture also has come, but still most of the processors offer small scale parallelism because most of the instructions are executed sequentially. Even though these processors are much cheaper, okay, they're simple, streamlined processor, but still they are unable to offer that kind of speed which are required for software-defined radio. Some of the state-of-the-art DSP processors, they come from Texas Instruments, analog devices like TMS 320 TC 16482 DSP processors operate 1 gigahertz. Then 30C 672X, they operate up to 300 megahertz. Similarly, ADSP, SARC processors, they're very powerful in fact. Even in fact, some VLIW architectures have also been incorporated in these processors. VLIW stands for very large instruction word. That means a number of instructions will be merged to a single instructions to exploit some limited parallelisms. But still, this drawbacks of VLIW architecture is, in fact, the memory utilization is very poor because not all the instructions will be requiring that peak instruction length. So here, if we just try to make the trade-off, perhaps we'll be achieving some amount of gain with a huge amount of cost. ASIC. ASIC is the application-specific integrated circuits. So here the cost is low because we have to manufacture in bulk. And ASIC is profitable when the total number of items manufactured more than 50,000. The power consumption is very low. And since the ASIC is designed for a particular applications, it will be very, very efficient, no doubt about it. Speed up will be very large because of fine-grained parallel processing, and use application-specific architecture that best matches the computations. That means it has been designed, it is tailored for a particular applications. But the problem, drawback is, the biggest drawbacks, no flexibility. If the problem changes slightly, design in it. That means entire thing will be obsolete totally. And huge amount of cost will be incurred for that. Because for developing ASIC, there are two costs involved. One is the NRE cost, non-recurrence expenditure. And second cost is depending on the number of chips, the cost will vary. It is something like Y equal to MX plus C. C is constant. So this C, the cost of C, this more will be selling, the C will be distributed on that. But now, the way the technology is changing very fast, your design has to be changed. And within that time, the entire product has to be sold. So this is a very, very tough and challenging job. That's why no economy of scale, non-recurrence engineering cost is very high. A long design cycle leads to longer time to market also, because ASIC design means it will take time. This entire VLSI chip has to be implemented, and we know what are the different phases of implementing a VLSI device. So that's why ASIC, from the economic point of view, is not very much accepted. So what you need basically? So we need to have a balance between speed and flexibility. ASIC has the speed, no flexibility. DSP processor, they have the flexibility because by changing the program, we can change the functionality. So from that point of view, it has the flexibility, but it doesn't offer the speed because the instructions will be executed one after one in a sequential fashion. That is the biggest drawback of the DSP processor, even the cost is low. So we have to find a balance between flexibility and efficiency. To eliminate the inflexibility associated with the ASIC, to overcome the speed limitation of the conventional DSP processors. So elimination of software approach to solve a given problem without losing the flexibility of the software. So it's a very challenging approach, So elimination of software approach, but at the same time, we have to keep the flexibility of the software and we have to retain the speed of the hardware. What is that? So that leads to reconfigurable architecture, possible alternative. So what is reconfigurable computing? So programming or configuring highly tuned hardware circuits to provide the functionality needed for the task. So it is a hardware device and it can be programmed to change the hardware. That is the reconfigurable. So an extension is, it is a manipulation of the logic within a programmable hardware device at runtime. So when the device is operating at that time, it can be configured to other. So to give an example, let's say a device, a hardware device now is functioning as a fast Fourier transform processor. Let's say the requirement is online requirement. It has to behave like a wavelet transform processor, and that can be done immediately by programming. So what is the advantage? So speed of the hardware is there because it's a hardware device. Is totally is operating in the hardware speed, but it has the flexibility of the software. So what is the advantages? Lower system cost, reduced time to market, because just by changing the software, by changing the program, you are changing the entire hardware. So for ASIC, the time incurred is not going to be here. So incremental design flow. Today you have designed something, and tomorrow you want to upgrade it. So simply by changing the software, you can upgrade it, and your hardware utilization factor will also be very high. So this is the programmable hardware. So what are programmable hardware? Let's see. Basically, it's the hardware device which can be changed by programming. Now, keeping this in view, Xilinx first came in the market in 1985. This was introduced by Xilinx. So Xilinx is a world leader in field programmable gate array. Excuse me. It offers a balance between flexibility and speed. So it offers the flexibility because it can be programmed, and this device can be programmed by a programming language called hardware description language. This hardware description language could be VSDL, could be Verilog, could be System C. So this offers a balance between flexibility and speed because it's a hardware device. It will operate in the hardware space, and it has the flexibility because you can change it by changing the program. So basically, it's based on lookup table, and lookup table replaces the actual logic gates. Just to talk about lookup table, like earlier, our concept of designing logic circuit was by OR gate, AND gate, NOT gate, etc. So for designing a complex logic circuits, we have to use huge amount of different gates. And now if you want to change it, you can't change it because once the PCB has been manufactured, the components have been soldered, then you can't change anything. But what is lookup table? Lookup table is based on the memory, and memory can be used as a logic device. It sounds funny, but it is. Entire truth table is stored onto lookup table. Just directly coming to that. Let's see first. What is the FPGA architecture? So FPGA architecture is based on configurable logic blocks, which consist of lookup table. Now, what is lookup table? Let's consider a logic functions to be implemented. So A, B, C, D, let's say these are input variable, and Z is the output variable. Let's say. Now, for 4 input variables, there will be 16 combinations, 2 to the power 4. And for each combination, output will be either 1 or 0 or something like that. Now, if we consider a memory, memory has what? Memory has some locations. In each location, some data will be stored, and locations are described by the address. Let's consider you have a memory 16 into 1 memory, means 16 locations, and each location will consist of 1 bit. So for 16 locations, you need 4-bit address lines. That means these addresses from 0000 to 1111, so different combinations will be there. That is the truth table. So you store this thing, and then you give a particular input. Let's say you have given 1010. That means in 1010 locations, what should be output for 1010 has been stored, and that will be getting. So that is a logic circuit. And if you want to change that logic circuit, you just change the contents of the program LUT. That means this is a software approach. So FPGA basically consists of some CLBs, some routing blocks, and some switches. So any complex hardware you can view as a combination of some building blocks. A number of blocks can do some sub-functions, and these sub-functions can be interconnected to make the system functions. That means you have a number of LUTs, and then these LUTs will be interconnected by some kind of switches. These are called routers. And definitely input and output blocks will be there. And other resources like memory, multipliers, global clock buffers, and this day boundary scan logic, that is a must by IEEE recommendations. So FPGA consists of some LUTs basically, and some switches and some IO blocks. Memory multipliers, they are optional. Even multipliers can be built by using the LUTs. But for making faster multipliers, dedicated multipliers are also kept, because FPGAs are mostly used for signal processing, image processing applications, and signal and image processing functions are based on adders and multipliers. That's why dedicated multipliers are also kept, and extra memory is there so that the image data and signal data, which are huge, they can be stored in this first memory. So this is an example of Xilinx Vertex 2 architecture. This green blocks are CLB, yellows are input output from where the data are coming in or data are going out of the FPGA, and some switches which are called the routing networks. So these CLBs will do some sub-functions and they will communicate among themselves through switches, and in that way a complicated functions can be divided into smaller functions which will be communicating among themselves and ultimately deliver the results. And input data will also be coming from the input. Now, FPGA design cycle: define a new project and enter the design using VSDL or Verilog or HDL, Advanced Hardware Description Language. Design can also be entered using schematic diagrams. Even some softwares are there. Simply you draw the schematic and which will translate to VSDL. That means input is the schematic of the hardware what you are going to design, and output will be hardware description language. Then you compile and simulate the design, find and fix timing violations. Sometimes, when you are designing, some logical error could be there, some timing violations could be there. So you just fix them. Then get power consumption estimates, perform the synthesis, which will be required, what we call design synthesis. Then, in fact, what you get, once you compile it, you will get a bit stream. So a bit stream file will be generated, and which will be downloaded onto FPGA, and FPGA will become that particular hardware. So for an example, let's say for communication applications, you want to design a modulation scheme and a demodulation scheme based on, let's say, amplitude modulations. So you write the program in hardware description language for modulations. Similarly, you do it for demodulations. And this program, after writing the program, you just check the program whether they're correct, and then you compile it, and compiler will generate the bit stream, and that bit stream will be downloaded onto FPGA, and FPGA will become the amplitude modulator and amplitude demodulator. So this is the FPGA design flow. So design specifications, RTL simulations, then synthesis, place and route. These days will be done by this software. But again, there's a problem associated with FPGA. FPGA are costlier compared to your DSP processors and others, and poor hardware utilization factor, because you can't buy an FPGA which matches exactly with your requirements. So it may so happen that many of the flow within the FPGA, flow in the FPGA means the total devices, number of LUTs and all, they'll be unutilized. So in that case, the utilization factor is poor. And high configuration latency. Configuration latency means in the real time, when it will be configured, it will take some time. So that latency is known as configuration latency. That is also high. And another thing, routing structure is very complex. A lot of switches will be there. Since using the same FPGA, you are making different kind of hardware. So there must be some provision for switches. By changing the switches, you will change from one applications to another applications. So this routing structure, in fact, they occupy 40 to 60% the resources totally, which is high, and power consumptions will also be high due to these routers. So FPGA dependent reconfigurable fabric utilization. So performance and flexibility, even though we are achieving, but it is at a very high silicon cost, and thereby the total cost will also be increased. So let's innovate something. Here, in fact, some of my PhD students, in fact, they are given this problem, and we have successfully come up with some solutions. That is the radio processor, and alternative to the conventional DSP or ASIC or FPGA. So there is a need to innovate an efficient reconfigurable architecture, which by eliminating the drawbacks of FPGAs and ASICs, by offering a balance between flexibility and reconfiguration latency. Hence, flexibility will be there. At the same time, the configuration latency should be very low, should not be high. Performance should be higher, cost should be low, it should be scalable. Scalable means today you are designing something. So let's say you are going to design 2 times powerful that by adding some other hardware also, it could be done. Low power consumptions. So these are the issues for making this radio processor, and which was done in the laboratory of MAKAUT. That time the name was WUT, and a number of my PhD students, they have achieved their PhD by working on radio processors, and a number of MTech students, they worked on that. So radio processor architecture will be under CPU control, is a totally reconfigurable architecture, and direct hardware execution of the DSP functions. And basic building blocks for these radio processors are, now if we consider any communication applications, so communication applications are basically what? Demodulator and modulator. There are different kind of scales. For all this, if we just analyze carefully, we'll find that these are the things which are required for basic building blocks. Digital local oscillator, that is must. That means direct digital synthesizers, sine cosine generator. Of course, modulator, demodulator, we'll see what are there inside that. Complex digital mixers, means complex multiplier. A plus JB into C plus JD. If we multiply, this is a complex multiplier, because when we will be multiplying two signals, basically we have to consider phase and magnitude both. So this is a complex. So A e to the power j theta into B e to the power j beta equal to what? So that multiplications are basically complex multiplications. That provision should be there. Some filter should be there, low pass filter. FFT computational unit should be there. FIR filter, trigonometric computation unit. We have to compute sine theta, cosine theta, and all. Let's say A plus JB is the final results. Then the magnitude will be root over A square plus B square, and phase will be tan inverse B by A. Then delay unit and memories. So delay units are implemented. Delay means z to the power minus 1 in mathematical term. So if input is Fn and output is Fn minus 1 in the discrete level, then we say that the system has unit delay. So that has to be implemented, and delay can be implemented by D flip-flop. So fundamental building blocks. Now, these are the basic building blocks. And what are the fundamental building blocks? So these basic building blocks, BBB, can be generated for fundamental units like adder, multiplier, delay, sine, cosines, square root units, etc. Then connecting these FUs in appropriate fashion, we can make different systems, different functions. So hence, reconfigurable soft processor can be conceptualized using a number of BBS and switches, so that by connecting these switches in appropriate fashion, different communication schemes can be made. So more precisely, we have a number of building blocks, basic building blocks. Using the basic building blocks, we can make fundamental units, and using the fundamental units connecting in particular fashion, we can make particular function, and we can call it soft processor. So translating the high-level description radio processor using HDL into bit stream. So since we are offering a new processor, what we are calling radio processor, there must be a language for that, which will be by which this radio processor can be programmed. So a translator will translate the high-level description written into HDL, hardware description language. So these bit streams, when downloaded onto FPGA, a particular connectivity is established. That's what for FPGA. But here for radio processor also, in fact, how it could be done, that we are going to discuss. For radio processor, let's consider 8 modulation demodulation schemes. There could be many. We are considering here for the sake of understanding. Let's say amplitude modulation, frequency modulation, BASK, BFSK, BPSK, DBPSK, QPSK, okay, OQPSK. So defense modulation schemes. Now, for all these modulation schemes, if we analyze one after one, we'll be requiring these basic building blocks: NOT gate, XOR gate, delay units, adder, multiplier, on-off level converter, serial to parallel converter, digital integrator, digital carrier generator, phase shifter. In fact, I would request our students, especially the undergraduate students, to take the communication scheme one after one and find out. I'm sure that you'll be lining up with this basic functional units required. And every communication scheme can be represented as a set of BBS. Like these sets are for amplitude modulations, C and M are required. Here you can see that what is multiplier, adder, this will be required. IC, PMA. So these are the different kind of BBVs will be required as a functional units. So to make the reconfigurable architecture, if we just make the union of all of these, that will make your radio processors. And by connecting them using the switches, we can make a different communication scheme. So for an example, let's say you want to make BPSK. So for BPSK, what is the connection pattern? That if you know, then from here you take those building blocks and connect them properly, it will become BPSK, or it could be BPSK. So from one radio processor, you can make any of the communication schemes. For example, architecture of the reconfigurable modulator using a BB. So this is the total architecture. In this architecture, if you see, all these basic building blocks are there. And just by switching means the multiplexers, changing them, you can reconfigure it to a particular communication pattern. That is the beauty of this architecture. So here for AM, you know, how the pattern will be there. That is shown by this arrow. So similarly for other one. So BPSK. And switching matrix for modulators. For AM, this is the switching pattern. For FM, this is the switching pattern. So just by giving the switching pattern, by changing them, it could be changed from one pattern to another pattern. That is one communication to another communication scheme. If we want to make, simply we have to change this DM, M1, M2, M3, M4, M5. These are the switches, means the input of the multiplexers, the select lines. By changing the select lines, the connectivity will be maintained. So here, similarly, architecture for demodulator is given and switch matrices. So we need to have an integrated development platform, also a software, which will help you to make these systems that we call integrated development platform. So this is the model of the reconfigurable architecture for SDR. Here, a CPU, it could be ARM processor, will have its own memory. So here, a configuration control logic, configuration memory. In fact, configuration memory will have the bit stream, and this is the reconfigurable radio processor. So let's say we want to make a particular communication scheme, particular modulation, demodulation. Chip will give a command to configuration control logic, and configuration control logic is an intelligent device which will allow the bit stream to be downloaded from the configuration memory onto configuration radio processor. So in turn, the radio processor will become that particular communications module. And DMA, using the DMA, a data, huge amount of input data that will be given. So this is the total model of the reconfigurable architecture for SDR. So radio processor description language, we have also innovated a language which is called radio processor description language. and it describes the input and outputs, describe the functions using the basic building blocks, describe the basic building blocks using fundamental units, describe the connectivity among the FUs and among the BBUs. So you have to mention to make a particular FU, what should be the connectivity among the BBUs, and getting the FU, what could be the connectivity among different FUs, and describe the parallel operations, like which operations can be done parallelly, which can be done serially. That's all. It's a very simple language, and a translator will translate this high-level description language of a radio to a set of bit strings for configuration. So download these bit strings, it will become a particular communication scheme. And these are the advantages. The software controlled hardware radio processors can be dynamically configured as and when required. Application software dynamically invokes pre-mapped hardware TSP functions stored as bit streams. No ASIC cost, no NRE cost, means there is no cost involved in non-recurrence expenses, and obsolete device cost, that is not there. So reduce interconnections complexity among the building blocks. So there will be very few blocks in fact, and interconnection complexity also gets reduced compared to FPGA, and in this way more efficient utilization of silicon can be obtained. And finally, in fact, the cost will also be very low. Now, in fact, recent times we are hearing about cognitive radio systems, which is one step ahead of the software-defined radio, but it definitely includes software-defined radio. It's that. So after the software-defined radio, which is slowly becoming into reality, cognitive radio and cognitive radio technology, this is in fact emerging as a major technology. So cognitive radio is a technology to use radio intelligently by recognizing the radio environment. So it's an intelligent device. So you are adding some intelligent onto software-defined radio to make cognitive radio. So what is that intelligence? We'll come to that. Consider this. There are different base stations, cellular base stations, WiMAX base stations, Wi-Fi. And Wi-Fi, as the signal strength of cellular and WiMAX is too low. Aggregate cellular, WiMAX, and Wi-Fi carriers to receive streaming data with high quality. So in fact, here, all these different base stations, different communication systems, they operate in different mode. But here, in fact, whatever is possible, you can utilize them. So selecting a particular device depending on the environment. So in fact, the idea for cognitive radio has come out of the need to utilize the radio system more efficiently. So whole idea is to utilize the radio system, the bandwidth more efficiently. So how this could be done, we'll come to that. There are three types. One is the heterogeneous cognitive radio. So heterogeneous cognitive radio select a system or aggregate multiple systems based on expected transmission rate. Depending on the transmission rate, you select a particular systems. So no system is nobody's intact, though as and when required, a particular system can be used. Like we must have noticed that when there is a huge traffic congestion is there, then we listen that message. All the routes in these lines are busy, please try after some time. But at that time, it may so happen that another base stations, another mobile systems, or another television systems which is operating on that bandwidth can be utilized if it is not used. Whenever that means, whenever there is a vacuum, whenever there is a bandwidth available, use that bandwidth. Then frequency sharing, you share the frequencies. Or load balancing. If the environmental changes occur, in fact, then there will be a problem. And use that other systems. If one system is having certain problems or some environmental problem, use the other radio systems. So cognitive radio definition. Cognitive radio may be defined as a radio that is aware of its environment. So intelligently, it will just keep track of the environment and the internal state. And with the knowledge of these elements in stored predefined objectives, that can implement decisions about the behavior. So depending on the environment, it will take the decision. In general, the cognitive radio may be expected to look at parameters such as channel occupancy, free channel, the type of data to be transmitted, and modulation types. It also look at the regulatory requirements. In some instances, in knowledge of geography, and this may alter. In many instances, it will use the software-defined radio. So accordingly, cognitive radio technology and software-defined radio, they are tightly linked. So the future of radio communication technology will be cognitive radio systems, which uses software-defined radio. The following, in fact, is a video from Nokia research that will help us to understand the effectivity of cognitive radio.